the neurons tend to be grouped together into layers. In other words, if you take this picture and you kind of connect it like this and like that and like that, this is kind of what you see when you zoom into the brain. There's a whole bunch of somas of neurons that are connected by all these axons and dendrites that are all interwoven and connected together. There happen to be about 6 layers in the cerebral cortex. Layer 1 does this, and layer 2 does that, and layer 3 does this other thing. And basically, they've been studying this for a long time, and there's about 6 layers that occupy most of your cerebral cortex. So it follows naturally that, hey, if we can build models that have lots of layers, wouldn't these models be more powerful than single layer models? Clever idea, right? And then wouldn't that give us something better than these linear models? Well, remember the equation, y equals mx. Let's forget the b right now just because it's simpler if we don't. Okay, what would it look like if I have 2 layers? Wouldn't that be y is equal to, well, if you have f of g of x, right, so we're going to have y is equal to m1 times m2 times x. Is this model more powerful than a linear model? Yeah, exactly. A matrix times a matrix is a matrix. Therefore, a linear model times a linear model is a linear model. That's kind of disappointing, right? So neuroscientists have been studying the brain and figuring out what happens in these neurons. And it turns out there's lots of reasons to suppose that it's kind of like a nonlinearity. For many years, the nonlinearity that everyone used was the step function. So when you take I'll just draw a single, this is called a perceptron. Here's what a perceptron does. It has lots of inputs. And inside this circle, we're going to put a binary step function, and then we have an output. So what a perceptron basically does is it says, hey, I'm going to look at all the values coming in, the features, things I'm interested in, and I'm going to give you an output, and that output is either going to be a 0 or a 1. 0, 0,1. Why? Because in the early days, they were doing this in circuitry, not in code. And basically, they were trying to build circuits that would work like the human brain because we wanted computer chips that were smart and intelligent because we all wanted to build commander data or something like that. Can you see why this, as a fundamental unit, might be an interesting or useful thing to investigate? Well, it was. So a lot of researchers took these perceptrons and started connecting them all together, trying to build the great big brain that would be super smart. And if you now imagine all these perceptrons are feeding into each other in multiple layers, then we've basically made the first attempt at creating an artificial brain. Only problem is this: how the heck are we going to train it? Turns out ordinary least squares only works if you have no nonlinearities. So if you get rid of these things, then it works great. As soon as you have nonlinearities, the calculus just gets unbearably complex. Especially if you have 3 or 4 layers, all of a sudden explodes into crazy stuff that Wolfram Alpha would struggle to solve, and then what you gonna do? So we needed a new method for training these things. It all gets very complicated. But here's the first solution, and this surprisingly works very nicely. So we'll take a bunch of perceptrons, and for simplicity, I'll just do 3 to 2 to 3 And we'll call that good so I don't have to do lots of drawing. But all of these values feed into all of these values. This feeds into that one. These all feed into that one. This feeds into that one. I usually draw from left to right because some researchers like to draw bottom to top and some like to draw top to bottom, and they fight holy wars over who's right. And well, if you go left to right, then everybody gets it and we can all get along. So I'll usually draw them going left to right. If you look at these pictures of the brain, it looks like whoever produced them liked either bottom to top or top to bottom. I don't know which. It's kind of ambiguous. But at least left to right, it's never ambiguous, right? Because nobody goes right to left. Of course you could, so anyway, I'll just go this way. Direction doesn't matter. It's really the math that matters. The implementation's nothing. But imagine a whole bunch of numbers feeding in here. So I start with a three-dimensional vector, and I'm going to produce two numbers, and they're going to be binary values, 0 or 1. And those values will get multiplied by something, who knows what, whatever the weights of these are, and they're going to produce something, and then that's going to be turned into a binary value, 0 or 1. And finally, I'm going to output some binary representation of something interesting, and if it's sufficiently interesting, that would be great. And this is kind of the first multi-layer. This is actually called a, wait for it, multi-layered perceptron. Except I don't think they put an ED on it. Let's call it a multi-layer perceptron. And the multi-layer perceptron is kind of the grandfather of the modern day deep neural network. The big kicker is how do you train it? So what they usually do, in fact, just for fun, let's make it a little deeper. But I'll do it the easy way. There, now it's deeper. If I have a bunch of data, I can take all of my, I'm just going to write the word data here and draw a big square to represent, this is a great big matrix full of data values where each row is a vector that I'm going to transpose so I can stick it onto these three elements. So I'm suggesting that I have 3 columns in my data here. And each row contains 3 elements, and I can put those 3 elements on here, and then I can feed it forward through my multi-layered perceptron, and it'll produce a 3-dimensional binary output vector. And very often we're interested in just binary. We might just want to ask the question, is this or is this not a picture of Marilyn Monroe? So let's just do a single binary unit so we can do a simple example. There's a neural network that could do it. What should the weights be? No one knows because calculus can't solve it, so we initialize it all with random values, and then we feed our data forward. And for every data point that we have, we get 2 values right there, right? So what we could do if we wanted is imagine that we initialize all the weights in this whole multi-layer perceptron with random values, and then we're going to run our data through all the way to the end, but not all the way, just to right there. And we're going to basically get new data that now only has 2 columns. And it will be all 1s and 0s. So 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0. There's no 9s in there. So now we have 2-column data because we fed it all the way through to the end here. And we also know what we wanted it to be because usually data comes with both features and labels. So we'll just copy those labels right over. You see that if we wanted to, we could train this last layer using ordinary least squares. So this is kind of a 2-step process. First, take your data and transform it by this random matrix. So it's going to just do stuff to your data. Who knows what it's going to do? Take your numbers and just munge them up in all kinds of funny ways. And then we've made new data. And we can use this data to train the last layer in the multilayer perceptron. Okay. If we were to do that, it actually works. In fact, there's no way you'd map to just 2 values. Let's map it to many values. So the network looks more like this. Then we'll map those all to 1. Now the problem's a little more interesting, because by the time I've mapped my data from just 3 values to 1, 2, 3, 4, 5, 6 values, chances are the information, the meaning encoded in this data is going to be preserved into 6 dimensions, right? Because I'm actually going to bigger rather than smaller. And let's see. Let me do a little demonstration here. I have a piece of paper. There's a piece of paper. Okay. This is a silly demonstration, but it's fun to do. I have here a bunch of X's in the middle. I'm just going to pull this down. And a bunch of circles all around it. Okay? Could you draw a line that separates all the X's from the O's? Some of you can't see that well. Let's see. I'll draw a representation up here so you can all see what I've done. Here's an X, here's an X, here's an X, here's an X. O, 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 O. Can you draw a line that will separate the X's from the O's? The answer, of course, is no, you cannot. What happens if you do linear regression to try to cause it to discern the difference? Well, it'll do its best. What will it do? Probably do something like that. Well, at least we managed to separate 3 of the O's from most of the X's. And if you measure the sum squared error for this data set, you know, it won't get 100%, but it's about as good as can be done, right? Well, what happens if the thing's highly nonlinear like this? We're mapping from 3 dimensions into 6 dimensions. Well, here in this silly example, I am on 2 dimensions, right? I'm going to take this 2-dimensional area and change it into 3 dimensions. Okay, now it's in 3 dimensions, and I've sent it into 3 dimensions in a really garbled, wonky way that I don't even understand. That happens if we initialize these weights with random values. Who knows what it's doing to our data, right? It's basically taking our data and bending it and twisting it and conforming it in all kinds of ways. But now imagine that I try to find a line that separates all the X's from the O's. There, I have ripped a straight line. And we open it up and we find I have all the X's on this piece of paper and all the O's are on this piece of paper. Yay. And what we have accomplished is a single linear layer can actually perform nonlinear separations if we first munge it up in all kinds of interesting, weird ways. Does that make sense? Well, that's kind of the whole intuition here is we don't really know what we're doing to the data. We know that we have a bunch of models. We know they're nonlinear because we've got these perceptron, these binary step nonlinearities alternating between linear layers. But if we alternate between linear layers and nonlinear transformations, then the data's getting mixed around and bent up and twisted in all kinds of funny ways. And finally, this last layer, it has 6 dimensions to work in, not just the mere 3. And in 6 dimensions, there's all kinds of ways you can slide that plane around, right? In 3 dimensions, you can only turn this way and that way, but in 6 dimensions, you can turn in ways you can't quite comprehend because there's 6 dimensions to work with. And so, turns out this model's more powerful than a single linear layer. And it doesn't require anything that wouldn't be super easy to code up. This is all just random stuff. Who knows what it does? It's just a bunch of random numbers and a binary step function. We transform our data and then we perform linear regression. And it turns out this actually works. Okay, so this is what's called a reservoir network. Reservoir network. And the idea here is everything up to this point is the reservoir. And then the final output layer is the only thing we actually train. And by training that part, we're learning how to map from this high dimensional space that's higher dimensionality than our original data even. And it does a decent job of learning data. Has anybody ever heard of a support vector machine? This is the fundamental key behind a support vector machine. That wasn't very clear English. This is the basic idea behind a support vector machine. Support vector machines use one other trick. They use a bunch of math to make this whole reservoir be computed much faster. They use something called the kernel trick, if anybody's ever heard of the kernel trick, and it causes a bunch of operations to cancel each other out, and they can actually take reservoirs into very, very large space with a small number of computations. And in some cases, it's even in infinite space. Doesn't mean it's infinitely effective or powerful, but it's... Anyway, support vector machines do something very much like that. But support vector machines aside, let's come back to just reservoir networks. Do you feel that you could code up a reservoir network right now if you wanted to, assuming your assignment 1 is done and completed and working? I bet you could. There's not a lot of work here. It really is just take your data and apply a bunch of weird random transformations to it. And then you get a new model. Okay. Now, not everybody's happy with binary step values. One problem with binary step is it only outputs zeros and ones, right? Wouldn't it be nice if we could output any number? Maybe values between 0 and 1, something like that. It would also be nice if the whole thing were differentiable, because then we can do some other operations such as iterative refinement of the weights. So people moved from binary step to the logistic function, which is basically a smoothed version of the step function. Let's take a look at the logistic function. 1 over 1 plus e to the minus x. Here's what the logistic function looks like. If we zoom out, you can see it basically is the step function, except it's smoother. Right? Instead of stepping in this region here, it's kind of gradually climbing up to there. So the logistic function became the next state of the art instead of binary steps. And now every unit here can output a value between 0 and 1. And that makes us feel better. And that makes the regression part have more numbers to work with. These are arbitrary values. And so it can now regress to data with less error, and we're all happy with that. For some reason, the term perceptron stuck. So a perceptron really means it uses the binary step activation function, meaning the nonlinearity function it uses is binary step. But a lot of people started using logistic functions as the nonlinearity instead. The logistic function, so each unit would be called a logistic unit, but the whole thing is still called a multilayer perceptron because nobody wanted to change their terms. Just cause. So still called the multilayer perceptron. Then we fast forward a little bit into the 1969, I think, is the first formulation of backpropagation. It didn't really become popularized until 1980 or so. There's a lot of heated debate over who actually invented backpropagation. I think Rumelhart is often credited with it, or he's credited with at least popularizing it. Werbos came out and said, oh wait, I invented it first because I did it I was at Harvard and he was working in economics and he had a reason to have invented it. And then it turns out a couple people came out after him and said, oh no, I invented it first and here's my publication to prove it. And it's still debated. Nobody knows for sure who the first backpropagation inventor was. Wikipedia has a claim on it. And we'll say they're right, because they probably are. Enough people have vetted it. Let's see, backpropagation, 1960. Oh, wow. Apparently someone in 1960 invented it.